Hi, have you ever wondered what would happen if you place a permanent magnet close to an already operating power supply? Well, you can ask me, why is it important? Is it something you would see in an application? Well, meter tampering is still an issue in some parts of the world, and depending on the strength of the magnet, its position relative to the transformer, and the converter design, power supply operation can be interrupted or halted entirely. Now, we can't do anything about the magnet, but we can certainly do something about flyback design. In flyback design, some considerations involve MOSFET and component selection, PCB design, controller scheme, but arguably, the transformer is at the core, center, so to speak, of being able to meet critical performance requirements. When designing your transformer, we usually use this equation. Li less than NBA. L is your inductance. It's dependent on your power requirement, your switching frequency, peak current available. I is the peak current I was talking about. And this is dependent on how much current your MOSFET can handle. And it's the peak current that's going through this winding, I peak. N refers to the number of turns, and this is dependent on your wire gauge, the window area that's available to you. A is the effective area of the core. This is dependent on core material, core size, and we have magnetic flux density B. When we design the transformer, usually we look at the core datasheet and we would find B max, which would help us design, considering the application, the ambient temperature, such that you won't fully magnetize the core during normal operation or saturated. Magnetic flux density B is defined as magnetic flux per unit area. In a transformer, this would be the flux. So these would be your flux lines. And like I said, this would be your effective area. I mentioned magnetic flux density, and sometimes you would hear this term, magnetic field intensity. These two sound the same. They might be confused with one another. Just to clarify, while B, magnetic flux density, refers to magnetic flux per unit area, this would be your magnetic flux. The area. H is a vector quantity, and it is used to quantify the field strength of the magnet. Let's say you have a current conducting rod here, which has a current I, and you have a point P, X, Y. This current conducting rod introduces magnetic field on point P, X, Y. H refers to strength, B refers to density. These two are related by this equation, where mu is the permeability of a material. Going back to how a permanent magnet would impact an already operating power supply, your equation for the magnetic flux density becomes something like this, where M here is the magnetization. And it's dependent on a few things, like the strength of the field that's caused by the magnet, its position relative to the transformer, and it's also dependent on the magnetic material of the core. Normally, we use ferrite cores because their properties are favorable for switch mode power supply operation. And ferrite cores are ferrimagnetic. Ferrimagnetic material react in such a way that when there's a permanent magnet placed close to a ferrimagnetic material, the internal magnetic dipoles align in an anti-parallel fashion, and what would happen is the resultant magnetic dipole moment actually decreases. And this implicates a decrease in the magnetic field. This equation you can rewrite something like this. And with a decrease in the magnetic field, a decrease in the magnetic flux density, you can also say that the permeability has changed. The material allows less flux going through the core. So if we look back on this example, for example, your magnetic flux lines will actually decrease as a result of the magnet. So you'd be working with less flux lines. Physically, the effective area of the transformer cannot change. Your number of turns cannot change. Your current, depending on your control scheme, could either stay the same or increase, but your magnetic flux density would decrease and your primary inductance would decrease. A decrease in the inductance, again, depending on the power MOSFET, your control design, could compromise your converter's ability to deliver power. If it does still deliver power, because you have fewer flux lines available in your core, it's easier to fully magnetize the core. It's easier to saturate the core. And that would result in warmer MOSFETs, a warmer transformer in general, which would compromise efficiency. You'd get increased thermals. It's non-ideal. Depending on your converter design, your drain current which would, let's say, ideally look like this. Could, in response to a permanent magnet, increase in frequency. Or depending on the position of the magnet, it could even actually look like this, where you can see it saturates. To address these issues, we've created two reference designs, DR708 and DR711. They both use PI's link switch XT2 900 volts, which has an integrated power device and controller that uses an on-off control scheme. This, along with proper transformer design, component selection, PCB layout, can help guarantee uninterrupted performance despite a potential reduction of the primary inductance of up to 50%. To learn more, visit power.com.